This is packet number 16, and it's problem number 11. And it takes us to a distant planet where there's a beautiful view, and once we admire that view, we begin to throw balls up and into the air to get a sense of its gravitational view. If we shoot a ball upwards from the ground at a rate of 100 meters per second, we can find that it takes the ball 10 seconds to land. Well, there's a little bit of information in there that 100 meters per second, that will be our initial velocity. So I'm going to say v sub 0 equals 100 meters per second. And it takes the ball 10 seconds to land. So if I take a little curve here, we know that balls going up and down are parabolic. Okay, so the ball's going to go up for a distance of some amount, but the velocity in here, so that slope in here, it starts off at 100 meters per second. It's going to slow down, and then it's going to speed up as it goes in a negative direction, but it goes up, comes down, and it takes 10 seconds to get there. So on part A, if the acceleration is a constant, we want to find an expression for the ball's velocity and height after t seconds. Well, the relationship between acceleration and velocity is the acceleration is the derivative of the velocity. So in order to go from acceleration to velocity, I have to take the antiderivative. And the antiderivative, since k is a constant, that would just mean that I would have the constant times the variable t, just to the first power, and then I have to remember that I have to add on my constant of integration, which in this case, instead of calling it plus c, I'm going to have plus v sub 0, because that's what c is when we're talking about velocity. It's that initial velocity. So I can substitute back in what the initial velocity is, and that's just 100. So to keep going, to find the height, well, the height in relation to the velocity, it too is the antiderivative. So the height function, the antiderivative of kt, where k is a constant, we have t the variable, that's going to be kt squared over 2. The antiderivative of 100 is 100t. And then again, we have to include our initial height. But our initial height, that's going to be 0, and it's 0 because we started from the ground. So we have these expressions, but we're asked to now solve for what k is, and we can do that in a couple of different ways. To solve for k, we know that since it's a parabola, that the distance when you throw the ball up goes, the peak of the distance has to happen at the halfway point between the two roots of the parabola. So it has to happen, the maximum has to happen at t is 5. So if I have the velocity at 5, that velocity, that slope right here, has to be 0. So if I put in 5 into our velocity function, I have 5k plus 100. And since that velocity has to equal 0, I can set it equal to 0, and I can solve for k. And so k would be negative 20. Another way to solve for k, again, we could use, instead of using the velocity function, we could use our height function, which is kt squared over 2 plus 100t, and there's no initial position because it's at the ground. And again, we know that that position function is a parabola, and that the function starts at t equals 0, at 10 it's back at 0, so we know that our height function at 10 has to equal 0, because we're back at the ground. And if you go about and solve that, and I'll leave the arithmetic to you, k would have to be -20. This is packet number 16, problem number 12, and we're told that the line tangent to the function 9 divided by x at x equals 3 forms a triangle with the coordinate axes, and this drawing here gives us a visual of it. Find the area of the triangle. So I've rewritten the function 9 divided by x to be 9x to the -1, and I'm doing that because I could work with this line, this tangent line here, a little bit to help us find that area. So in order to try to find that tangent line, I'm first, of course, going to need the derivative of the function at the point of tangency, which they've given us x is 3. So the derivative of this would be -9 x to the -2. And if I evaluate the derivative at 3, I'm going to have -9 divided by 9 is -1. Again, in order to work with the line of tangency, I actually have to find the line itself. And I know my x coordinate, but I need to find the y coordinate of the point of tangency. So I can find that by substituting 3 into our original function. And that would give me 3, 3. So I have the point 3, 3 to work with. And if I go ahead and use point slope form, I can find that equation of the tangent line. So y minus 3 equals the slope times x minus 3. Now to move on to trying to find the area of the triangle, well, area is base times height. So the length of the base, I'll call this down here, this red line here, my base, and so I have to find that length, and I have to find the height of the triangle. In order to do that, that means I need to know where the x and y intercepts are, and I can find that out using our equation of our tangent line. So at this y-intercept, I know that x has to be 0, and then I have to solve for what my y is. So if I put in x is 0, it ends up that y is 6. To find out where our x-intercept is, I'm going to go back here. This looks more like a b than it is a 6. So, okay, so for the x-intercept, well, I'm going to clean up. I'm going to change the point slope form of our equation to the slope-intercept form. Might make the computation just a little bit easier. Okay, and for our x-intercept, that means we have some value x, but our y is 0, so I need to find out what that x is, and in order to do that, I just have to set this equal to 0. turns out that x is 6 as well. Then overall, if I want the area, I just need to, area is 1/2 the base times the height, forgive me. So the area of the triangle is 1/2, 6 times 6, so the total area is 18.